Good morning or good afternoon, Shona. Depends what time you're watching my investigation video. My name is Mitchell Ferguson. Today I will be discussing geometry in the real world and how mathematical applications relate to the construction of bridge building. The use of geometry is vital in the modern and ancient worlds, especially in the mathematical application of bridges. Without geometry, would there even be any such thing as a bridge? In this investigative report, the mathematical application of bridges will be discussed and analysed and how they relate to the real world, STEM, science, technology, engineering and mathematics, and the impacts bridges have on the environment and modern day life. Ancient societies are known to have the experience of bridge building. However, the Romans have left lasting a legacy of durable, usable structures that have lasted for more than 2,000 years. Some of the remarkable features are the technology and the utilitarian diversity. This is from Lewis Spence, 2016. However, over many years, bridges have become more complex, more weight-bearing, and mathematically more complicated. But this is needed for the quick-growing population of humans. Bridges, big, small, or medium, all incorporate the mathematical concept of geometry. But why is this? Geometry in bridges is to help in stabilising and creating a strong bridge structure to support large vehicles and other heavy equipment that humans use on a daily to get from one place to another. There are different types and shapes of bridges found all over the world. The 5 main bridges include truss bridge, an arch, cable, beam, suspension, and cantilever. These are all types of bridges and will be used depending on different terrain and length that needs to be covered. Here is a quick overview of what each bridge looks like. So up the top left, we got the simple beam bridge. Below that, we got the arch bridge. On the right of the arch bridge, we got the cantilever bridge. Below the cantilever, we've got the cable bridge, and just below the cable bridge is the suspension bridge. The 4 most common geometric shapes involved in bridges are triangles, arches, connector plates, and symmetry. These geometric applications are all vital in every single bridge. Triangles are used as shapes for bridges because they can evenly distribute weight throughout the construction of the bridge. Although triangles are mainly used in truss bridges, they can be important in all bridges. This helps create a stronger and more weight-bearing bridge. Arches are another vital part in the geometry of bridges. According to the PBA.org, arch bridges are one of the oldest types of bridges and have great natural strength. Instead of pushing straight down, the weight of an arch bridge is carried outward along the curve of the arch to support each end. Thirdly, connector plates can come in different shapes, such as squares or triangles, and they are used to strengthen the connecting points on a bridge, says Jennifer Elrod, 2017. Lastly, is the symmetry of the bridge. As well as being a geometrical application, symmetry is also a mathematical application used in bridge building, and it focuses on a half of a figure being the mirror image of its other half, which also adds to the strength and weight bearing which we're after of the bridges. Through my investigation, I found out that there are many mathematical applications in bridges. Geometry obviously being one, but there are many others. That can be found especially in construction of bridges. Mathematics and mathematical equations are vital in building bridges because measurements must be precise to avoid disaster and maintain a cost-efficient job. Mathematical applications that are involved in bridges include trigonometry, Pythagoras' theorem, symmetry, geometric shapes, patterns, and also the equation for bridge parabola, which will be discussed in a later stage. These mathematical applications prove and show that building of bridges requires many different types of applications, but all come together to be able to construct a bridge. Here I have a quick view of a mind map that I made, which shows what links off with the mathematical applications of bridges. This one will be discussed in a later part of the video. The first 2 mathematical applications that will be analysed are trigonometry and Pythagoras' theorem because of their similarities and how they relate to the application of bridges. Trigonometry is to do with the measurement and configuration of triangles, which is pointed out before are very useful in construction of bridges. A study by Robert Kuhlmann, 2015, who was a live science contributor, states that trigonometry is a branch of mathematics that studies relationship between the sides and angles of triangles. Trigonometry is found all throughout geometry. Further still, trigonometry has outstandingly indicated relationships to other branches of mathematics, in particular complex numbers, infinite series, logarithms, and calculus. However, how does trigonometry relate to bridge construction? Trigonometry allows triangles to be measured and placed in a specific part of the bridges to help in stabilization and strength, which is what we're working on with the bridges, which allows everyday people to get to and from places, as we know. The next form of mathematical application is Pythagoras' theorem, which is also a calculation of triangles, but mainly focuses on right-angled triangles and reinforces bridges the same way as trigonometry, which helps in stabilization of the bridges. More weight bearing as well, that's what it helps with. So here I've written out the two equations for Pythagoras theorem and geometry. As we got Pythagoras theorem over here, which is obviously our right angled triangle, there's our equation. A squared plus B squared equals C squared. Over on the right side is trigonometry. Got the sin and the angle equals opposite over hypotenuse. Cos angle equals adjacent over hypotenuse. And tan angle equals opposite over adjacent. Here's our triangle here that we were trying to figure out. Secondly, to include the other three mathematical applications, patterns, symmetry, and geometric shapes, they're all kind of similar when it comes to construction of bridges. Patterns are important in bridge building, because they add to the aesthetic of the bridge, but also certain patterns, such as an X or a triangle shape pattern, increases the weight bearing of the bridge. Patterns then lead on to geometric shapes, such as the triangle that was spoken before, and also squares as the connector plates, which are also known to provide strength for the bridges, all about enhancing bridges. Lastly, symmetry is probably most important out of these three mathematical applications. As mentioned before, symmetry is a mirror image of another half. This mirror image is very important as it allows for weight bearing evenly distributed throughout a bridge. Lastly, but most definitely not least, is the equation for bridge parabola. This is the most complex out of the mathematical applications written about in this report. This equation is perfectly shown in the Sydney Harbour Bridge, as it defines both the lower arch parabola and the upper arch parabola, which are calculated to provide strength of a bridge using mathematical formulas. I'll show you an example of this equation right after, which helps you understand what they've done when building the Sydney Harbour Bridge. Here is the equation for bridge parabola. This one's on the Sydney Harbour Bridge. We got y equals negative a, brackets open, x take h, brackets closed, to the power of 2. Here I've done a quick sketch of the lower arch parabola and the upper arch parabola. The last aspect that is going to be talked about in this investigation is STEM. STEM is an educational program developed to prepare primary and secondary students for college and graduate study in the fields of science, technology, engineering, and mathematics. Hence the STEM. In addition to subject-specific learning, STEM aims to foster inquiring minds, logical reasoning, and collaboration skills. Here I have a mind map that I'm about to talk about. As you can see, we start off with the mathematical applications of bridges. We stem out into 4 yellow points. Shapes involved, geometry of bridges, mathematical applications, and STEM, as we've just spoken about. Off STEM, we see engineering, technology, mathematics, and science. Off mathematics, we see the mathematical applications involved, trigonometry, equation of bridge parabola, Pythagoras theorem, geometry. Science, force, tension, compression, and load. And technology, advance in technology since ancient times, as bridges have become more quality and weight-bearing to deal with the heavy loads of today. Shape involves, we got things such as squares, triangles. Geometry, we got triangles, arches, connector plate, symmetry. Symmetry connects to mathematical applications such as trigonometry, geometry, geometric shapes, Pythagoras theorem, patterns, equation for bridge parabola. And then as we link off those, we got Pythagoras, a squared plus b squared equals c squared. Trigonometry, sin, angle equals opposite, cos, opposite. as we've discussed before. And lastly, we got equation for bridge parabola, which is y equals negative a, open brackets, x, take h, close brackets, squared, plus k we've got. We've spoken about the positives. However, man-made equipment and structures also have disadvantages, especially when it comes to the environment. Disadvantages on the environment include lessening of the ecosystem's ability to produce and provide for an organism, habitat loss, less chance of survival for organisms, loss of animal protection in homes, and noise pollution. These disadvantages seem to sound disastrous, but what if there was never such thing as this invention? Like the bridge, what would that mean? Without bridges, humans and animals alike wouldn't be able to cross rivers, oceans, dams to get to places to see or to see family, friends. This is why bridges are so important in everyday modern life. Hope you enjoyed my video. Peace.